At $30,000 per unit, the NVIDIA H100 is a piece of nanometer-scale civil engineering, a sprawling physical layout of 80 billion individual components. This jagged metallic rock is purified silicon. The manufacturing pipeline begins with ordinary silica sand, which is chemically stripped of its oxygen until only these solid blue and silver crystals remain. These rocks are melted at 1400 degrees Celsius, pulled into a single massive ingot, and sliced into 300-millimeter wafers. Diamond saws and chemical polishers refine the surface to a sub-0.1 nanometer flatness. At this scale, even a microscopic surface deviation would prevent the circuitry from printing correctly, destroying the value of the wafer before the first transistor is ever built. Because the wafer is a blank slate, engineers use electronic design automation tools to map the exact positioning of every gate and interconnect. This design is etched into a photomask, a piece of high-purity quartz glass layered with chrome geometry. This serves as the physical stencil that will define the chip's circuitry. Once the terabyte-scale design file is finalized and sent to a foundry like TSMC, the project reaches a milestone called tape-out. Tape-out represents a high-stakes transition. Once the physical fabrication begins, any error in the logic requires a multi-million-dollar manufacturing restart rather than a simple code update. Inside a TSMC Class 1 cleanroom, the air is filtered to a degree where dust is virtually non-existent. Wafers move between machines on automated overhead tracks to prevent any human-borne contamination. Traditional ultraviolet light cannot print features smaller than its own wavelength. To reach the scale required for the H100, the foundry must use extreme ultraviolet lithography, or EUV, which operates at 13.5 nanometers. Generating this light involves striking a falling droplet of molten tin with a high-powered laser. The tin instantly vaporizes into a burst of plasma that emits the required EUV wavelength. Because EUV is absorbed by traditional glass lenses, the light is guided by a series of specialized mirrors. These mirrors bounce the light through the photomask stencil to project the circuit pattern onto the wafer. This process of vaporizing metal to create sub-visible light is the specific mechanism that allows us to pack 80 billion transistors onto a single processor. The H100 is a 3D structure built over 100 layers. Materials are deposited, etched into microscopic canyons, and filled with copper for vertical interconnects. To make it conductive, the foundry uses doping. High-velocity ions bombard the grid, creating regions necessary for electrical flow. A high-heat annealing phase follows, which repairs the structural damage from the ion bombardment and locks those foreign atoms into the crystal lattice. These distinct atomic regions form the gates of 3D FinFET transistors. By applying a small voltage, the chip can precisely control the flow of electrons between these regions. This forced injection of foreign atoms serves as the spark of life for the chip, turning a piece of inert sand into a series of functional logical switches. Once fabrication is complete, the wafer moves to testing. Under these objective lenses, microscopic needles probe each die to identify defects and determine yield rate. An H100 die measures 814 square millimeters. Because of that massive size, only about 80 can fit on a single 300-millimeter wafer. At this density, a single speck of dust landing on a die during the month-long process results in a catastrophic financial loss. The working dies are then cut and fused alongside stacks of high-bandwidth memory onto a silicon interposer. This packaging step connects the compute engine to its memory with massive bandwidth. Modern AI compute relies on this risky integration. By grouping these separate dies onto a single interposer, the system achieves the data speeds necessary for large-scale model training. This thermal heat map shows the finished module during its final trial, the burn-in test. The hardware is pushed to its thermal and frequency limits to ensure stability under maximum load. This data determines the binning of the chip. If a package survives the highest stress levels, it is sold as a premium $30,000 H100. If it falters, it is downgraded to a slower, less expensive variant. This single processor is the result of 3 months of 24/7 robotic fabrication, using machines that take a year to build and dozens of freight trucks to transport. The software driving the AI revolution is tethered to this physical reality, a sequence of precisely controlled thermal and chemical reactions that force light and atoms into the shape of a processor. This is how we convert common sand into the engine of the future.